Okay, thanks for the opportunity to share about our work. This is joint with Ray Lee and Eugene Tang. So first, I'll briefly outline what the talk will cover. So I'll first give a brief introduction to quantum codes, including both stabilizer and subsystem codes. And then I'll talk about how they're constrained by geometric locality. This will lead us to the main question, which is what is the locality parameter trade-off for subsystem codes? And then finally, I'll present our results, which will include the main result and some intuition for the proofs and a discussion of optimality. So first, quantum codes. So a major problem with building quantum computers is that physical qubits are noisy and imperfect. So one way to address this problem is to use error correcting encodes. You can encode k qubits of logical information into some greater number n of physical qubits. And then if the number of errors on our physical qubits isn't too large, then we can use a procedure to recover the information. A specific class of quantum codes that we study are called stabilizer codes. So stabilizer codes are defined by stabilizer group, which is an abelian subgroup of the n-qubit polygroup that does not contain the negative identity. Each stabilizer group is generated by a set of independent generators. The stabilizer code is then the set of all quantum states that remain invariant under the action of a generator. So we often describe a quantum code by three parameters, n, k, and d. Here, n is the block length of the code and is equal to the number of physical qubits you use. K is the dimension of the code and is equal to the number of logical qubits you get. And d is the distance of the code, which corresponds to the number of errors that your code can correct. So if you have distance d, you can correct almost up to d, basically d minus 1 erasures. And for stabilizer codes, the distance is equal to the minimum weight of a non-trivial logical operator. Here, the weight of an operator is just the number of tensor components that are not equal to I, and a non-trivial logical operator commutes with all the stabilizers, but it's not a stabilizer itself. And so as an example, here we have some physical qubits, and I'm going to define a stabilizer generator by saying that the action on all the physical qubits is the identity, except for acting with poly z on the 4 qubits in the top left. And so since there are 4 qubits that are being acted on by something that's not the identity, this would be a weight 4 stabilizer generator. Great. Okay, so let's move on to subsystem codes. A subsystem code is a decomposition of a stabilizer code into two parts, A and B, which we call the logical part and the gauge part. If the logical part has dimension 2 to the k, and the gauge part has dimension 2 to the g, then we can interpret a subsystem code as a stabilizer code that can encode k plus g logical qubits, but only actually use k of these to protect information. So what we mean by this is that we just don't use g of the qubits, and we'll call them gauge qubits, and errors on these qubits just like don't matter. A subsystem code is described by its gauge group, which is generated by the stabilizer group, along with the logical x and z operators associated with just the gauge qubits. And finally, one thing we know is that a stabilizer code is just a subsystem code with no gauge qubits. So subsystem codes are a generalization of stabilizer codes. Now, the main difference between stabilizer and subsystem codes that are relevant for us is in the classification of logical operators. So for subsystem codes, we have two types of logical operators. They're called bare and dressed. A bare logical operator commutes with all the elements of the gauge group, and they act trivially on gauge qubits. On the other hand, a dressed logical operator commutes only with all the stabilizers, and these might operate non-trivially on gauge qubits. And since we don't care about what happens to the gauge qubits, like the errors on them just don't matter, the distance of a subsystem code is defined as the minimum weight of a non-trivial dressed logical operator. And again, we note that for a stabilizer code, there is no distinction between bare and dressed. So that's all we really need to know about quantum codes. Now let's define locality. So what we're interested in studying is codes under locality constraints. And this is of interest because physical architectures for quantum computers favor local interactions in low-dimensional embeddings. So what does this mean? So first, just kind of informally, if you have a stabilizer code, you need to put your qubits somewhere in space. And then if you want to correct errors, you need to do some measurements of the stabilizer generators, which is easier if the qubits are close together. So roughly speaking, when we mean embedding, we mean we put the qubits somewhere. And when we mean local, we mean the qubits are close. So formally, this is what we mean. An embedding is a mapping of the qubits of your quantum code into d-dimensional Euclidean space, where the pairwise distance between qubits is at least 1. So this requirement that the distance be at least 1 sets the length scale of the problem. Otherwise, you could just shrink your embedding as much as you want. So here on the right, we have an example. Just suppose you have some n physical qubits. You can embed them into a 2D lattice, and this would be like a valid embedding. So what is an interaction? We say that two qubits interact if they are both in the support of the same stabilizer generator. And if we continue to use the previously used example of the weight 4 stabilizer generator, we would say that the 4 qubits acted on by Z are interacting or participate in an interaction. And finally, a local interaction is just one with a constant of 1 length. So for example, the 4 qubits that are interacting in the top left corner, these are local interactions because even if we increase the size of our code, which would correspond to kind of increasing the size of the lattice, these qubits remain neighbors, right? They're not being moved. So their interaction length stays the same. On the other hand, if you were to take a qubit from the left corner and say it interacted in some stabilizer generator with a qubit in the bottom right corner, as you increase the size of this lattice, these qubits will get farther and farther apart. So this would not be a local interaction. This would be non-local. Well, it turns out that locality constrains the quality of the stabilizer code. So it was shown that local stabilizer codes embedded on a lattice in d dimensions must have d at most n to the d minus 1 over d, and kd to the 2 over d minus 1 at most n. So the constraint on d is called the bt bound, and the constraint on k and d together is called the bpt bound. And we just note for d equals 2, this just says that d is O of root n, and kd squared is O of n. So the BT and the BPT bound, it's really a barrier for the quality of a local stabilizer code. And so if you want to, if you want to get better parameters beyond the BPT bound, you need to sacrifice the concept of locality. And so, a natural question to ask is like, how non-local do these better codes need to be? So this is a question that was posed by Basman Krishna, and they broke it down into 2 parts. So the first part is how many non-local interactions do you need? And the second part is how long do these have to be? So you can kind of see that this is like a way to quantitatively characterize how much non-locality you have in your quantum code. Okay. And so this answer was answered kind of in an earlier work and generalized by us. And that we found an optimal locality and parameter trade-off for stabilizer codes. And this is what it is. So every d-dimensional embedding of an NKD stabilizer code has at least m interactions of length at least L, where m is max KD and L is this big expression over here. And the important thing to notice just here is that this is just really like a trade-off, right? You can see that like as you increase the code parameters, you require more and more non-locality, both in the interaction count m and the interaction length L. And so as an example, you can consider taking an asymptotically good stabilizer code. Well, if you wanted to embed this into 2 dimensions, just plug in the parameters and d equals 2 into the theorem, and then it tells you that, well, then you need an embedding. Every embedding would require at least n interactions of length root n. And so this is kind of like the worst possible because whenever you have n qubits, you can always embed them into a root n by root n lattice, and then the interaction length cannot be any length longer than the length of the diagonal, which is root n. So this is like asymptotically like the worst possible. And moreover, this trade-off happens to be optimal. We also find constructions that saturate the bound, and so really this is kind of like a complete answer to the question of like how non-local, how much non-locality do you need in a stabilizer code to achieve certain parameters. Well, then the next question is then, can we generalize this to subsystem codes? Do we expect anything different? And it turns out that subsystem codes are able to violate the BPT bound. So Bravish constructed 2D local subsystem codes with K and D both O over root n. And you can see how this breaks the 2D BPT bound. But even though the subsystem codes can break the BPT bound, they are still themselves constrained by locality. Ravi also showed that local subsystem codes embedded in a d-dimensional lattice must have d at most n to the d minus 1 over d, and kd to the 1 over d minus 1 at most n. And so this is in some sense a generalization of the BPT bound. You can here are the parameters for BPT. The bound on the trade-off for just d is the same, but the trade-off with k and d has a slightly different exponent in the d. And so this leads us now to like our main question that we'd like to answer. Our main question is, what is the locality versus parameter trade-off for subsystem codes? So before we were able to find like these optimal bounds for stabilizer codes, we'd like to see if we can do the same for subsystem codes. So specifically, how much non-locality is required for the subsystem code to exceed Bravi's bound? And moreover, how does the amount of non-locality required compare with stabilizer codes? So recall that like the way we answered this was by providing like an interaction count that was required and an interaction length that was required. So we're going to try to like to provide like values for those two, for the interaction count and length, and then compare them to the corresponding values for stabilizer codes. So here's our result. So this is a locality parameter trade-off for subsystem codes, and it goes like this. So it says that we say that every d-dimensional embedding of an NKD subsystem code has at least m star interactions of length L star, where m star is max KD and L star is this big expression here. And then so immediately we kind of see some like similarities with the bound on stabilizer codes. First of all, there's the same bound on the interaction count, and the required length of interaction is similar. So like if you were to look at this expression like closely, you would see that it's basically the same in a lot of parameter regimes, and it's only like a smaller amount of interaction length in like a very restricted parameter range. As an example, just to make this more clear, you can consider an asymptotically good subsystem code with a 2D embedding, just as we did for the stabilizer code. So if you plug into the theorem here, again, you would require at least n interactions of length root n, which was exactly the same as a stabilizer code. So what we see really is that subsystem codes don't really save on locality compared to stabilizer codes. Like you don't really make much of a benefit. So I guess in one sentence, yeah, subsystem codes also require a lot of non-locality, which is, I guess, perhaps unsurprising given how similar the BPT bound was with Bravi's bound. Okay, so now I'll talk a little bit about the proof and the technique of how we achieve this. I'll try to compare it as well with the analogous techniques for stabilizer codes. So with stabilizer codes, we analyze we analyze locality using correctable sets. And a correctable set is intuitively a set that can be erased, uh, and the code that can still recover the information. So for stabilizer codes, this just corresponded to for a subset of qubits being correctable, if and only if no non-trivial logical operators were supported on it. And analogously for subsystem codes, we have that a subset of qubits U is correctable if and only if no non-trivial dressed logical operators are supported on it. We should remember that subsystem codes also have this like other like type of logical operator, right? Like the bare logical operators that act trivially on the gauge qubits. So we kind of have some sort of form of correctability or just some sort of labeling for like in the analogous situation where we don't support any bare logical operators. Who say that a subset U is dressed cleanable if it does not support any non-trivial bare logical operators. And again, this is like a strictly weaker form of correctability because a subset that is correctable supports no dressed logical operators, which means it supports no bare logical operators, which means it's dressed cleanable. And so, like, why are these concepts useful? Well, there's a lemma by which would probably used implicitly that if we let Q be the qubits of an NKD subsystem code, and we partition Q into two sets A and B, where A is dressed cleanable, then K, the dimension of the code, can be no bigger than the size of B. So intuitively, you can kind of think of this like, well, if I like don't need A, if I can like kind of erase A or get rid of A in some sense, then the information has to be like stored in B. So like it makes sense that like the size of B is something that constrains the dimension of the code, which is how much logical information you can store. So this leads us to our like strategy. If we assume we have an NKD code with a small amount of non-locality, so we have like maybe has like a certain number of long interactions where those are defined based on the parameters from before, and if we can find a sufficiently large dressed cleanable set A, then the fact that K is less than or equal to B can give a contradiction, and then we have to conclude that our code or our embedding of the code actually has more non-locality than that. So this is how we construct our lower bounds. And the key part here is that we need to be able to construct a large dressed cleanable set A. I guess I want to comment here that like the only difference between this and stabilizer codes is that stabilizer codes you have an ABC lemma, so where you can partition your qubit into three sets A, B, and C, and then if A and B are correctable, then K is less than or equal to the size of C. So this gives like you have like an extra set kind of to work with, that that's what kind of what gives the difference in the bounds between subsystem codes and stabilizer codes. So how do we construct large sets? We use like four properties of correctable or address cleanable sets that hold. So let Q be the qubits of an NKD subsystem code. Then one, this is called the subset property. So if a subset U of Q, if U is a subset of Q is correctable, then any subset W is also correctable. This makes sense because if we can delete a set U of qubits, then we can surely delete a smaller set of qubits and still be correctable. Second property is called the distance property, and it says that if we have a subset of qubits that has size less than the code distance, then this is a correctable set. This is also kind of clear just from the definition of the code distance. The code distance is the number of erasures that the code can tolerate. So by definition, if there are less qubits than the code distance, then we can erase them all and still be correctable. The third property is called the union lemma, and it says that if we have a set of decoupled correctable subsets, here decoupled just means that the subsets are disjoint and disconnected, meaning they don't interact, then their union is dressed cleanable. And so this is a way of taking individual correctable sets and kind of like combining them together to get an overall bigger set. And finally, we have the expansion lemma. And this says that if U and T are correctable with T containing the boundary of U, where the boundary of a set of qubits is just the qubits that interact with qubits outside of the set, as well as those qubits themselves, then the union of T and U is correctable. So really this just says that if a set and its boundary are both correctable, then together the whole set together is also correctable. And so if you think about what these lemmas are, really, the distance lemma is kind of a way to get a initial correctable set. You just pick any set that's less than D, and this is correctable. And then if you use the expansion lemma, if this starting set is sufficiently small, then its boundary is probably pretty small too. And then so you can use the expansion lemma to kind of grow a bigger correctable set. And then maybe once you've done this as much as you can, maybe eventually the boundary gets too big, you can kind of grab a bunch of these together and use the union lemma to tie them together. And then you have like this really big correctable set in the end. This is kind of like the general idea. But this like naive idea like doesn't always work. So so sometimes sometimes it might be necessary to apply both the union lemma and the expansion lemma maybe at like the same time or like alternating. And then this is a problem for subsystem codes because the expansion lemma requires that you take your input be a correctable set, but then union lemma outputs an only addressed cleanable set, which is weaker. So you can't actually like use them alternatingly. And I'll explain a little bit more about what I mean in the next slide. So previous proof generalizing the BT bound, which is the one that gives the trade-off between D and N only, required alternating usage of the union and expansion lemmas. So what we did really was we wanted to show that the whole set of qubits was correctable. And this means that the code is that if the whole set of qubits is correctable, then B has size 0, which means that the dimension has to be, it cannot be any greater than 0, which contradicts, the assumption that our code is non-trivial. And so what was necessary was we kind of had to recursively divide our set of qubits into smaller pieces, and then apply alternating usages of the union and expansion lemma to kind of stitch it back together and get a big correctable set in the end. And this is not possible because you can't use the expansion lemma after using the union lemma with subsystem codes. So we came up with a new method that involves expanding in one dimension at a time and switching only when we get stuck. And one can show that this method, it does work. Like you don't ever like get stuck and you can't like keep going in a different direction or something. And so we basically avoid using the union lemma at all. And we only use the expansion lemma to grow our like really big set and eventually conclude that all the qubits are correctable. And so this is like a new proof of the BT bound that like wasn't around previously. And so yeah, this is like the main difference between our current work and like the previous work with stabilizer codes. Okay, now finally I want to talk about how our bounds are optimal. So our result covers all statements of the form every code needs at least m interactions of length at least L. And why does this? Well, the first thing that is false is that we cannot make any statements that say all codes must have strictly more than m star non-local interactions. This is because of the existence of asymptotically good LDPC codes. Each of these codes have at most O of n interactions, and O of n is also O of m star because K and D are both O of n. So there are codes with at most O of m star non-local interactions, and actually more than just non-local interactions in general. So this is like a saturation of that part of the bound in a very extreme fashion. In a similar way, you cannot make the statement that all codes must have at least one interaction of at least something that's bigger than L star, what L star is, the L star that we found previously. And this is because we construct subsystem codes with no interactions of length bigger than L star. And the idea here is you just concatenate a wire code, which is a geometrically local subsystem code that saturates Rabi's bound, with a good LDPC code. And it is a kind of way of optimally getting the trade-off between locality and parameters. Good LDPC codes have the best parameters, but poor locality. And so if you just constrain their interaction lengths using a geometrically local code, you can kind of get like the best of both worlds. And so because we have these extreme ways of saturating the bound, our whole bound ends up being optimal. Okay, so now I'll just summarize the talk. So what we did is we found optimal lower bounds for the quantity m and length L of interactions required for the subsystem code to achieve certain parameters. We did this by reasoning about correctable sets and arbitrary embeddings into d-dimensional Euclidean space. And finally, we conclude that this generalizes Rabi's bound and tells us that subsystem codes do not have a substantial advantage over stabilizer codes with respect to geometric locality. Thank you.